It's pretty amazing when you think about it, how a cut on your finger just heals, or how a broken bone can knit itself back together. Deep inside you, right now, there's this incredible microscopic construction crew hard at work. Your cells are absolute master engineers, constantly repairing and rebuilding. But what happens when the damage is just too big? What happens when the job is too much for them to handle on their own? Well, that's the fascinating challenge we're going to dig into. It's a really serious problem in medicine. I mean, for most fractures, your body's healing process is just a work of art. But for those really severe breaks, we're talking about what doctors call critical size defects, which are gaps bigger than about 25 millimeters. The body's own repair crew just can't build a bridge across that gap. And that condition, known as a non-union, means the bone just plain fails to heal. And that's a huge issue for patients and doctors alike. Okay, so to really get how we can help the body heal these massive injuries, we're going to go on a little journey. We'll start with how implants have a secret language, then we'll zoom way in to see how individual cells actually feel their environment. We'll find the on switch for bone growth, explore a pretty serious biological dilemma, and then see how engineers are designing and literally modeling the future of healing. Right. So to fix those big, critical-size defects, surgeons use something called a scaffold. It's basically a biomaterial that acts like a bridge, giving new tissue a place to grow. But here's the kicker. Its success isn't just about being strong, it's all about communication. The implant has to speak a language that your cells can actually understand. And what's so wild is that this isn't a chemical language, like a drug. No, it's a physical one. Your cells are literally responding to physical cues from the implant itself, cues that tell them what to do, what to become. So the billion-dollar question is, what exactly are they sensing? Let's dive into the micro world for a second. Your cells, they're not just these passive blobs floating around. Not at all. They are active, you could almost say intelligent, agents that are constantly poking and prodding their surroundings. They are, in a very real way, tiny engineers, feeling out the construction site before they even think about starting to build. And this amazing ability has a name. It's called mechanosensing. All that fancy word means is that it's how cells literally feel the world around them. They can tell if a surface is soft, like fat, or kind of firm, like muscle, or rock solid, like bone. And this sense of touch, it's the main instruction they get. It tells them exactly what they're supposed to do. So how in the world did they do it? Well, think of a cell as having its own internal scaffolding. That's called the skeleton, which gives it its shape. Then it reaches out with these tiny sensory fingers, called focal adhesions, to grab onto a surface and give it a little pull. By feeling the resistance, how much that surface pushes back, the cell knows exactly how stiff its neighborhood is. Now, this creates a really fascinating puzzle for designing implants. It's a total Goldilocks problem. If the implant material is too stiff, way stiffer than your natural bone, it ends up carrying all the weight and stress. The bone around it gets lazy, a thing called stress shielding, and it actually starts to dissolve. Not good. But if the implant is too soft, it can't give the new bone the stable foundation it needs to grow. It has to be just right. So the cell feels the stiffness. Great. But how does that feeling get turned into an order to start building bone? It all happens through a signaling pathway. And the foreman on this whole cellular construction site are two proteins. One's called YAP, the other's TAZ. These two are the ones who give the final go or no-go for making new bone. It works like a surprisingly simple on-off switch, and stiffness is what flips it. When a cell feels a soft surface, YAP and TAZ are basically told to hang out in the cell's main area, the cytoplasm. You can think of it as the break room. Bone growth is switched off. But when that cell feels a stiff bone-like surface, a signal goes out that lets YAP and TAZ move into the cell's nucleus. Let's call that the front office. And that's where they switch on the genes for building bone. This whole operation is managed by something called the hippo pathway. To put it simply, when the surface is stiff, the tension inside the cell switches off the hippo pathway. With the guards gone, YAP and TAZ are totally free to march right into the nucleus and get to work, activating the genetic blueprints for bone construction. It's this beautiful, direct line from a physical force to a genetic action. But you knew there had to be a catch, right? In any good story, there's a complication. It turns out the exact same signal that we desperately need to build bone can also cause a massive problem, because that stiffness signal isn't just heard by the bone-building cells. Your immune system is listening in too. And this, right here, is the core dilemma. In your bone-building cells, that stiff surface signal activates YAP and TAZ, and you get wonderful tissue regeneration. That's a huge win. But in your immune cells, like macrophages, that exact same signal activates YAP and TAZ and triggers a massive inflammatory response. The immune system can start to see that stiff implant as a dangerous invader, leading to chronic inflammation and ultimately rejection of the implant. So all of a sudden, the engineering challenge gets incredibly tricky. How on earth do you design a scaffold that sends the build bone signal to one type of cell without sending the attack signal to another? How do you create a material that speaks the right language to the right audience and only at the right time? For years, finding this just right design has been a really slow, really expensive process. The old school approach was basically just trial and error in the lab. And sure, we can build these super detailed computer models that simulate every little thing, but they take so much computing power that they're just not practical for designing an implant for a specific patient. We needed a smarter, faster way to do this. And that brings us to the breakthrough. Researchers have developed a brand new kind of computer model that's kind of like a weather forecast, but for bone growth. It lets them predict how bone will grow on a scaffold over time, but without that massive computational cost. It's called a homogenized model. Now, instead of simulating every single tiny strut and pore of the scaffold, which takes forever, the model uses some really clever math to just calculate the average properties and behavior over a larger area. It's basically a smart shortcut that captures all the essential physics of healing without getting lost in the microscopic weeds. So what does this actually mean? It means that with these fast, predictive models, engineers can now design and test thousands of virtual scaffold designs for your specific injury. They can tweak the stiffness, the shape, the porosity, all on a computer, and find the perfect design before a single piece of material is ever 3D printed. This is what opens the door to truly personalized medicine. Ultimately, the whole goal here is to bridge the gap between two different worlds. This isn't just about mechanical engineering, and it's not just about cell biology. It's about mechanobiology, designing materials that are perfectly tuned to the precise mechanical and biological signals your body needs to heal itself. And this leaves us with this incredible vision of the future, doesn't it? Are we heading towards a world where, after a really bad accident, a doctor can scan your break, run a quick simulation, and then 3D print a personalized implant that is perfectly designed to speak your body's own unique language of healing? The science says we're getting closer every single day.